In the last video, I showed you how to calculate a p-value using the example scenario of watching your friend collect blaze rods. We saw that the p-value was defined as the probability of getting a result at least as extreme as the one we observed, given that the null hypothesis is true. Since our friend collected 67 out of 100 blaze rods, this corresponded to the probability of killing 100 blazes and collecting at least 67 blaze rods, assuming our friend wasn't cheating. It's worth now taking a step back to think about why we calculate p-values in this way and not some other way. Why, for example, do we calculate the probability of getting a result at least as extreme, and not just the probability of getting exactly the number of rods that we see? To understand why, let's imagine for a second that we did calculate p-values this way, using the probability of getting an exact result. My goal is to convince you that the p-value we calculate this way is not particularly useful. This effect is easier to see at higher sample sizes, so let's switch up our data. Imagine your friend instead killed 1,000 blazes and collected 501 rods. Unlike the data in our last video, this seems like a totally reasonable number of rods to get if your friend wasn't cheating, if the drop probability was 50%. And so you likely wouldn't be too suspicious of them here. Intuitively, this means that we shouldn't expect a significant result from this data. But if you calculate the p-value in this new way, as the probability of getting exactly 501 rods under the null hypothesis, it's only 2.5%. We'd conclude that our friend encountered quite a rare outcome. Does this mean that they had to get very lucky and point to evidence of cheating? Well, obviously not, because as we said before, 501 rods is a totally reasonable account to get without cheating. While the outcome of exactly this many rods might be rare, it's not surprising. That's because at 1,000 blaze kills, there are just so many potential outcomes that the probability is spread out, and all the outcomes are rare. You can imagine that this spreading out only gets worse as the number of potential outcomes gets larger. To take a more extreme example, imagine rolling a die with 1,000,000 sides. No matter which number you roll, that number only had a 1 in a million chance of coming up. But you wouldn't be surprised at seeing such a rare event occur, because all possible events are rare. If, on the other hand, you rolled a 1 or a 1,000,000 on this die, you would be quite surprised, since these are the most extreme values you could get. When we compute p-values, we in some sense want to quantify how surprised we are by the data, not how rare it is. Intuitively, we should be more surprised by seeing data at the extreme ends of the probability distribution. So a good way to measure our surprise is to calculate the probability of getting results at least as extreme as our data. Notice how by defining the p-value in this way, it only gets small when our observed results are extreme, and not when they're more central. Quick side note, in our example we only care about extreme values on the right side of the distribution, because we only expect a cheater to increase the drop odds, not to decrease them. This makes our test one-sided, and I'll discuss the other case where we care about both extremes, a two-sided test, a little bit at the end of the video. This reasoning about exact values becomes even more obvious in the case when our data is continuous, when it can take on any decimal value rather than just whole numbers. Say your data consists of measuring heights. Because heights can take on any decimal value, we can measure height with any precision that we want, that is, to any number of decimal places. The further out that we go, the more unlikely it is to find a person of that exact height. For example, what's the probability of measuring this exact height? The height is so precise that the probability of a match is basically 0. And yet, if you had some super accurate tool to measure height, you certainly wouldn't be surprised to get a result that looks like this. Because we can have arbitrarily high precision, it's essentially meaningless to talk about exact probabilities for continuous data. This is another point in favor of using at least probabilities. What I just showed you is the intuitive answer to our question. But there's actually a more mathematically rigorous reason to define p-values this way, which has to do with controlling the probability of a wrong significance result when the null hypothesis is true. It turns out, as I'm about to show in the next section, that by calculating the p-value in this way, we can ensure that this probability is equal to the significance threshold that we set for our hypothesis test. So, let's now see why this is true. Remember that the goal of a hypothesis test is to compare two different hypotheses, or two different worlds that we might live in, and try to guess which hypothesis is the true one. We then assume that the null hypothesis is true and calculate the p-value as the probability of getting a result at least as extreme as our observed result, if this assumption holds. Last video, we said that if the p-value is lower than some threshold, usually 5%, we conclude that our result was unlikely to have happened in the null world, and so we reject the null hypothesis in favor of the alternative hypothesis. On the other hand, if the p-value is not sufficiently low, then we say that we fail to reject the null hypothesis. We never say that we accept the null hypothesis, since our hypothesis test can't actually provide evidence that it's true, only that it's false. Why? Well, it's hard to prove that the drop probability mu is exactly some value. Our friend might have cheated by changing mu by a very small amount, say to 0.51. If so, it would be hard to detect this change. We'd likely get around 51 out of 100 rods, and so our calculated p-value would be pretty high, even though the null hypothesis is false. We'd probably need to observe way more than 100 blaze kills before we had enough data to notice the difference from mu equals 0.5. In fact, no matter how close your data is to a probability of 50%, I could just claim that our friend changed it to an even closer amount. So to completely accept that mu is exactly 0.5, we need a large enough sample size to rule out even the slightest increase by our friend, which is impossible with a finite dataset. So, every hypothesis test either rejects the null or fails to reject the null. And remember, there are two possibilities for the world we're living in: the null hypothesis and the alternative hypothesis. Hopefully, our conclusion lines up with the truth and we guess correctly. But there are two ways that our hypothesis test can give us a wrong conclusion. One way is if the null hypothesis is true, but our test rejects it. This is called a type 1 error, or a false positive. On the other hand, if the null hypothesis is actually false and we fail to reject it, we call it a type 2 error, or a false negative. Remember that there's some randomness to the data that we collect for a hypothesis test, so a natural question to ask is, what are the probabilities of these errors occurring? In other words, if the null hypothesis is true, what's the probability of collecting data which rejects it? And if the null hypothesis is false, what's the probability of collecting data that fails to reject it? These probabilities are called the type 1 error rate, or false positive rate, and type 2 error rate, or false negative rate, and they're important values to understand when interpreting the results of a hypothesis test. The calculation of the type 2 error rate is a bit beyond the scope of this video, and it also depends on exactly which alternative world we live in. That is, it depends on just how much our friend increased the probability mu by. By the way, the flip side of the type 2 error rate is called the power of the test, just in case you want to look up how to calculate it. But we'll instead turn now to calculating the type 1 error rate. The question we're asking is, assuming we live in the null world, that is, if the null hypothesis is true, what's the probability that we make a type 1 error by rejecting the null hypothesis? To put it in terms of our example, if our friend was not cheating, what's the probability that they'd get lucky enough for us to conclude that they were cheating? Recall from before that researchers usually reject the null hypothesis when the p-value is less than some threshold, usually 5%. But let's generalize now and say that this threshold can be any p-value, which we'll call alpha. For visualization though, I'll stick with an alpha value of 5%. So, we'll decide to reject the null hypothesis if p is less than alpha. If the null hypothesis is true, then we'll make a type 1 error when this happens. So what we want to know is the probability that p is less than alpha when the null hypothesis is true. How can we determine this? First, let's let x prime represent the number of rods that our friend gets out of n blazes. Remember that the p-value is the probability of getting at least x prime rods, so the p-value is the probability to the right of this line in our probability distribution. Notice how the p-value gets smaller the further to the right this line gets. So as we move it right, there must be some value of x where p first becomes just less than alpha. Let's denote this value of x by x alpha. If the x prime line is at or to the right of the x alpha line, our p-value will be less than alpha, and our test will be wrongly significant. We call this region the rejection region, because if our data x prime lies within it, we reject the null hypothesis. And remember, its area is basically as close to alpha as we can get without going over. Since we're assuming the null is true in this case, if our data lands in the rejection region, our test will be wrong, a false positive. So what's the probability of this happening? We're essentially asking for the probability that x prime is at least x alpha under the null hypothesis. But under the null hypothesis, x prime simply follows this binomial distribution. So to find the probability that it's at least x alpha, We just add up the probability to the right of the x alpha line. But remember, we defined x alpha so that the area to the right was slightly less than alpha, so the probability is also slightly less than alpha. However, it's easy to see that as our sample size n gets larger, our x values are finer grained, and so we can get this area closer and closer to alpha. Or we can imagine that if our data took on decimal values, then we can find x alpha so that this area is exactly alpha. So it's usually sufficient to simply say that this probability is equal to alpha. Although if you want to be rigorous, keep in mind that for whole number distributions, alpha is technically just a close upper limit. What we've shown here is that the probability of a false positive under the null hypothesis is just our significance threshold. In fact, this is the mathematical justification for why the hypothesis test is defined the way it is. To show you how, I want to reset the definition of a hypothesis test for a second, and imagine how we might come up with its rules from scratch. Remember, our goal with this test is to determine which of two competing hypotheses is true. Each hypothesis that we consider has an associated probability distribution, but only the null distribution is actually known because the alternative hypothesis doesn't specify exactly what mu is. So we have to compare our observed data, x prime, to this null distribution. To compare, we'll define some region of this distribution as the rejection region, call it R, so that if our observed data x prime lies within the region, we'll reject the null hypothesis, and if not, we'll fail to reject. Now, we just need to figure out two things. One, how big should this rejection region be? And two, where in our distribution should we put it? To answer question 1, imagine that the null hypothesis is true, and think about the probability that our data x prime lands in the rejection region. Remember that under the null hypothesis, our data x prime follows this distribution. So this probability is exactly equal to the total heights of the rejection region bars, the size of R, since that's just the definition of a probability distribution that we saw last video. But also, if x prime is in R, then we reject the null hypothesis and get a false positive. So this probability is also equal to the type 1 error rate. The size of the rejection region, that is, the heights of all the bars, directly corresponds to the type 1 error rate. The smaller we make our rejection region, the less likely we'll be to get an incorrectly significant result when the null hypothesis is true. But there's a trade-off here, because a smaller rejection region also means we're less likely to reject the null hypothesis when it's false, leading to a higher type 2 error rate. So picking the size of R is a compromise, which depends on how much we care about each type of error. To answer our second question, remember that the alternative hypothesis specified that mu was greater than 0.5. So if the alternative hypothesis were true, we'd expect values at the right side of the distribution to occur more frequently than under the null hypothesis. Since we want to reject the null in these cases, we want x prime to be in R, so we should place R as far to the right as possible to maximize the chances of rejecting the null when the alternative is true. This is the same as minimizing the chances that x prime is not in R, aka a false negative. So placing R all the way to the right has the effect of minimizing the type 2 error rate. To recap, we've created a rejection region which was sized to control the type 1 error rate, and positioned to minimize the type 2 error rate. This is exactly equivalent to how we formulated hypothesis testing in the previous video, only now we've motivated that formulation using the type 1 and 2 error rates. You can see that since the size of the rejection region is the type 1 error, choosing how big to make R corresponds to picking a value for alpha, the significance threshold for our test. Then, x prime landing in the rejection region just corresponds to the p-value being less than alpha. Hopefully now you can appreciate that choosing an alpha value of 0.05 is just saying that 5% is an acceptable compromise on the type 1 error rate. If we set alpha to be 5%, then we can guarantee that when the null hypothesis is true, we'll wrongly reject it only 5% of the time, or 1 in 20. On the flip side, this means that if we perform 20 tests in the null world, we'd expect one of our conclusions to be wrong. More generally, if we perform m independence tests with threshold alpha, all in which the null is true, the number of false positives we expect to get is m times alpha. This formulation leads nicely into another very important concept in hypothesis tests, called multiple testing. We can imagine how a fraudulent researcher might take advantage of the false positive rate to conjure a significant result even when none exists. This person could observe every Minecraft player on a single day, say observing 1,200 players. If none of them are cheating, then on average, hypothesis testing would identify 60 of them as cheaters with a threshold of 5%. In fact, we'd expect the luckiest player to have a p-value around 0.08%, which would seem like conclusive evidence of cheating. Or, even worse, say our fraudulent researcher had a particular vendetta against a single player. They could observe 20 runs by that player and only include the luckiest run in their analysis, making it look like the player got luckier than they did. Or, alternatively, they could analyze all runs, but instead of just observing blaze drops, they could perform 20 different tests for 20 different possible ways to cheat. Even if the player wasn't cheating, on average we'd expect one of these tests to be a false positive at a 5% threshold. So either way, our researcher could provide statistical evidence that anyone was cheating, even if they got average luck. What's wrong here? How is this different from us testing our friend? The key is in the number of tests we performed, that is, the number of datasets we observed. If we perform just one test by observing only our friend's blaze drops across all runs, then we wouldn't expect a significant result if they were innocent. But perform a whole bunch of tests, and suddenly we're basically guaranteed at least one significant result. This is known as multiple testing, or multiple comparisons. See, an implicit assumption of hypothesis testing is that the data we see was sampled randomly. If a researcher only shows us the most damning data they collected, then it's no longer randomly observed, and they can make it seem like they found a significant result where none truly exists. This is an example of what's called p-hacking, and it can happen both intentionally and unintentionally whenever the data in our study was not truly observed randomly. But what if there's a legitimate reason for us to perform multiple tests? How do we correct for the increased number of false positives? Well, we'd clearly need to lower our significance threshold to make it more stringent. This process is called multiple testing correction, and there are many different methods depending on the assumptions you make. But the simplest and most stringent way of doing this is just to divide your significance threshold by the number of tests you performed. This is called the Bonferroni correction, and it has the nice property that the expected number of independent false positives will be equal to alpha, and so always less than 1. In this two-part introduction to hypothesis testing, I stuck to the example of collecting blaze rods. But hypothesis tests can take on many different forms, like the drug testing example from part 1, depending on the form of our data and our hypotheses. The example that I used in this video is called the binomial test, after the distribution that our data followed. And in the drug testing example, we would use something called a 2-proportion z-test, if you want to look it up. Here are some examples of other types of tests that you might encounter, depending on the data and hypotheses that you're testing, and there are lots more. But all of them calculate a p-value the same way, as the probability of getting results at least as extreme as the observed results, given the null hypothesis is true. There are so many details about hypothesis testing that I had to leave out of this video, to keep it from becoming a whole semester's worth of statistics. I'll briefly mention a few of them now as footnotes, so you can explore further if you're interested. First, remember that in our example, our alternative hypothesis only considered the possibility of mu changing in one direction. That is, we hypothesized that our friend would cheat by increasing the drop rate rather than lowering it. I did this for simplicity, but it also makes sense for our specific example, because we never expect someone to cheat by lowering the drop rate. This means that our alternative was one-sided, and so we performed what's called a one-sided hypothesis test. However, in many cases of hypothesis testing, we don't have an obvious reason to suspect that the parameter we're investigating moves one way or the other in the alternative hypothesis. For example, when testing a new drug, while we hope that the drug increases the probability of recovery, it's certainly also possible that it decreases it. If we want to consider that the value can shift in two directions, then we formulate our alternative hypothesis as a does not equal statement, known as a two-sided alternative. Now, when we calculate the p-value, we need to take into account that extreme values can occur on both sides of the null distribution, which in this case has the effect of doubling the p-value we calculate. Equivalently, we can also think of a two-sided test as splitting the rejection region into two regions, one for each side, which minimizes the type 2 error rate under the two-sided alternative. Second, in this example, our observed result only consisted of one number, the number of rods collected. This made our p-value calculation very straightforward, since we could use this single number as a measure for how extreme our result was. In practice, however, most collected data consists of many numbers, like, for instance, a list of heights from two groups of people. To calculate a p-value with data like this, we need to somehow capture how extreme or unexpected our data is in a single number. To do this, statisticians calculate a summary of the data called a test statistic, a number which, roughly speaking, measures how extreme the data is. For example, one way you might imagine doing this is by finding the difference in average height between the two groups, which you'd expect to be close to zero under the null hypothesis that there's no difference. Test statistics are calculated so that they follow a known distribution under the null hypothesis. In our scenario, we only collected one data point, the number of rods dropped, and so that data point was our test statistic, which we called x prime. We saw that under the null hypothesis, x prime follows a binomial distribution. In other types of hypothesis tests, you might come across other test statistics which follow other distributions under the null hypothesis of that test. For example, you may have heard of a z-score, sometimes called sigma, a test statistic which measures how much a sample or set of samples differs from a known normal distribution. Under the null hypothesis, the z-score that you calculate from your data follows a standard normal distribution, with mean 0 and standard deviation 1. Other examples of test statistics include t-statistics, which follow a t-distribution, and chi-squared values, which follow a chi-squared distribution. You might notice that these distributions also differ from our example in that they are continuous distributions. In the Minecraft scenario, our test statistic took the form of the number of rods collected, which will always be a whole number. So the probability distribution of this statistic is discrete, meaning it consists of a collection of distinct possibilities. However, when we deal with data that can take on any decimal value, like say an average of data points, the probability distribution that we use is continuous and looks like a smooth curve. Calculating p-values using a continuous distribution turns out to involve calculating the area under its curve, which involves a bit of calculus. Third, it's very common to confuse the p-value with the probability that the null hypothesis is true. These are two distinct probabilities. Remember that the p-value is the probability of getting data at least as extreme as the data you observe, assuming the null hypothesis is true. I think the simplest way I can convince you that this is different is to show you the relevant XKCD comic. Take a second to pause and read it. Here, the researchers correctly calculate a p-value of 0.027, but it would obviously be ridiculous to conclude that there's a 97.3% chance the sun exploded. What we failed to consider is the prior probability of the null hypothesis being false. That is, how absurdly unlikely we think the sun is to explode before we look at the data. You might wonder if it's actually possible to calculate this other probability, the probability that the null hypothesis is true. And it turns out to depend on how we actually think about what it is that probability is measuring. So far, we've been using the frequentist philosophy, where, very roughly speaking, probability measures the frequency of some event occurring in a large number of random trials. While this is useful in predicting the outcome of future events, we can't assign meaningful probabilities to unknown events that have already occurred. So, for example, either our friend cheated or they didn't. This isn't a random trial that can repeat multiple times, it's just a fact of the universe. So the frequentist probability is either 0 if our friend cheated, or 1 if they didn't, and we just can't tell which is the case. So the frequentist answer to this question is unknown. But alternatively, we could interpret probability as measuring the strength in your belief that an event occurred or will occur. In this framing, known as Bayesian probability, the probability actually depends on our personal point of view, and can change if we see new data which will update our confidence in some event. So this probability is possible to calculate using Bayesian statistics as long as we're willing to specify the belief we had before looking at the data. But this is a topic for another time, and I'd really recommend the video by 3Blue1Brown that I've left in the description. Thank you for sticking around till the end. There are lots of p-value explainers out there, but not many that focus on the why, about justifying hypothesis testing from first principles. There's way too much about this topic to fit in only 2 videos, and you've probably noticed that I haven't even discussed how we actually compute p-values from the distribution. I left this out because 1, it requires a bit more mathematical background before getting into, and 2, the number crunching is what most statistics classes will teach you, And so I wanted to focus more on the rationale behind why you're crunching the numbers in that way. If you're curious about learning more, I've left some links to further viewing in the description. And one day, I might get around to making a full series on probability and statistics. It's a super interesting and important topic, but riddled with misconceptions and unintuitive results that are hard to wrap your brain around. But given how long it's taken me to put together these animations, don't expect it anytime soon.